In this video, I'm going to show you how I apply a microcontroller in a real-world project. The problem: creating a constant vacuum source, much like you would see with a compressor, keeping a constant positive pressure in the tank. In a compressor, you have the compressor motor, and then generally you'll have a tank that's right below it, or on the side of it. And the motor is constantly pumping the motor, and you'd also have a pump here, is pumping air into the tank. There also exists a pressure switch that turns the motor on when the pressure inside the tank is below, say, 85 pounds per square inch, psi, and would turn the motor off if the pressure in the tank equals 115. And this is generally why you hear with compressors that are used in the construction industry for nailing or whatever, you'd only hear the motor every now and then. And that's because it's trying to maintain a minimum of 85 pounds per square inch of pressure in the tank. The challenge here is to make the vacuum work in a similar way. So you'd have a motor, you'd also have a pump, and you'd also have a tank. And in contrast to let's put tank here, and this is positive 85 psi to 115 psi. So in contrast to the compressor, the tank and the compressor has positive 85 psi to 115. The tank would have a vacuum, and it would have, let's say, 0 psi to whatever equals the atmosphere, the outside atmosphere. Outside atmosphere is generally around 14, I think it's 14.7. So there's 14.7 psi outside of this tank, and anything below 14.7 psi would be a vacuum. Most conversion programs would show you a negative psi, and negative psi would be generally psi that pounds per square inch that is less than the atmospheric or the pounds per square inch outside of the tank. So if there's a psi that is lower than the outside pressure, let's say 13, then you're actually in the negative region with respect to the outside of the tank. Other common units associated with tank pressure for vacuum is inches of mercury, millimeters of mercury, psi, torr, and kPa, which is kilopascals. In this video, I'm generally going to be talking in inches of mercury, and every now and then I may give the equivalence of what the psi is and maybe the kPa, because some of the sensors use the kPa, some sensors use inches of mercury and psi. Most sensors you'll find use psi or kPa, kilopascals. So the key to making this work is to make sure that the motor is running when it needs to be running. And in inches of mercury, a good vacuum for my application, which is pick and place, is between 25 inches of mercury to 15 inches of mercury. 0 inches of mercury would just be equal to the atmospheric pressure. So we want to get some vacuum, and then have it between the top vacuum that my vacuum pump can actually reach, is 25 inches of mercury, and then the lowest vacuum should be at 15 inches of mercury. I could just use the motor and pump as a vacuum pump, and then just continually run the vacuum pump and use that as a continuous vacuum, but there's really no sense in wasting valuable pumped air, which is valuable vacuum. I mean, it's good to sort of use a tank to save the efforts of what the pump is doing. So using this method, we'll be able to save some electricity with the motor, and also because my vacuum pump is relatively loud. I mean, it's probably around 60 decibels. I'd rather not have that ambient noise happening during the use of the pick and place machine. I'd rather have a relative quiet around that machine most of the time. So I am electing to add a sensor and a switch to the motor. In my current setup, I'm actually just hooking up the motor and pump to the tank and creating vacuum, and when it reaches 25 inches of mercury, I physically turn it off. And then when it goes down to about 15 inches of mercury, which is a good enough time span of doing a pick and place for a couple of boards, I actually have to remember to turn it on. So I'm going to replace that effort of me turning it on and turning it off with a more automated microcontroller and switch, pressure switch, and using a pressure sensor. You'll have a difficult time finding a pressure switch for vacuum on the internet. Generally, it ranges in the hundreds of dollars. So I'm electing to make one myself, which is from a discrete component of a pressure switch, which looks like this. And you'll see that there's a port on the top, and then you can use these 4 pins on this side. This is a Freescale sensor, and it has a silicone substrate inside and a die inside, and the silicone gets pulled up with some leads that are flexed in a way that will change the resistance inside. There is a place for voltage and ground, and there is a voltage output, which this would be an analog output, and that would be connected to the ADC of the microcontroller. I have yet to see a setup on the market that actually has this configuration using a motor, pump, and tank for a vacuum system with a pressure switch. Really, it's not that, it's more of a specialized application, and it doesn't really exist pretty much on the internet. Because I've looked, and it might be available for laboratory applications, and generally you have to get into specialized catalogs and things like that to find them, and I really don't have the time, and it would be actually faster for me to build it myself than to find it online, and most likely this stuff will cost a lot of money. Compressors are already out there, and because they're not as specialized, it's almost a commodity when it comes to construction, and a lot of people out there that have a standard compressor, and these are relatively cheap. Even the sensors, the pressure sensor and switch are very inexpensive because it's in high demand. So this is actually easier to build on your own, and it's a lot cheaper to build on your own. The sensor itself is actually relatively expensive. It's about $12, and the microcontroller is relatively inexpensive. The tank you can get at essentially any auto parts store, or even I believe Home Depot or Lowe's may have it. And the vacuum pump, there's a lot of varieties of vacuum pump, and you can find those. You can actually use a compressor inside of a tank, pumping the air out of the tank. And it has to get air somewhere, so it would have to suck the air out of the tank, but you would have to create your own tank in that scenario. I'm electing to use a vacuum pump. Mine I think cost about $100 or something like that, but there's other ways you can do that. This can also be done without using a microcontroller, with maybe some discrete components like resistors and transistors. But I find the use of a microcontroller much better in this particular scenario, because I'll be able to expand the functionality if I want to use it for something else other than just the maintaining a constant vacuum. I could use it to expand the functions of the pick and place machine in other ways. So to review, we have a motor, a pump, and generally this is just one unit. It's a vacuum pump. We'll have a tank. This will be connected to the tank, sucking air out of the tank, and the tank will go to the nozzle of the pick and place machine. We'll have a relay that connects to the motor, and a relay allows the motor to turn on and off using the 110 volts system that I have, and the microcontroller and pressure switch will control the relay. The pressure switch will also have a line to the tank measuring the pressure of the tank. When the pressure goes when the pressure goes above 15 inches of mercury, or approximately -7 psi, the motor will turn on. If the motor has reached 25 inches of mercury, which is approximately -15 psi, and this is relative to the atmospheric pressure around it, so it's not really a negative psi, it's a negative psi relative to the atmosphere outside of the tank. And when the tank reaches 25 inches of mercury, the motor will turn off. In this project, I will also be adding the LCD, and it will show the, I don't know, maybe inches of mercury or psi or whatever, and it can also show the low and the high values that the motor will turn on and turn off for the pressure relative to the pressure in the tank. We can also create maybe 2 potentiometers or maybe a couple buttons to increase or decrease the low and high values, so we can tweak the pressure in the tank, our low pressure in the tank and our high pressure in the tank, to determine when the motor will turn on and off. And we could do that with using 2 more analog to digital channels. In this first part of the video, I will first do it by just plugging in the numbers in the program instead of adding potentiometers, and then I will add the potentiometers to the program, to the circuit. To make the prototyping a lot easier, I created a breakout board, essentially, just using a perf board. I took the only 4 leads that we're going to be using. We're not going to be using 5 through 8, we're only going to be using 1 through 4. And I put it on the perf board, and on the underside, I have a header to make it a lot easier to plug into the prototyping board, the breadboard. You can actually plug the SMD leads inside the breadboard, but it's really difficult to get a good signal out of them, and you have to keep moving them and jiggling them to get a good signal. So let's go ahead and connect this to the breadboard. We can connect it to the oscilloscope, applying power first to it, and then putting another lead from the oscilloscope to it, and see what kind of values we get when we are creating a vacuum from this port on the top of the sensor. So according to the data sheet, this particular sensor will be able to sense a range of -115 kilopascals to 0 kilopascals, and that's the same as -16.7 psi to +2.2 psi. And the voltage range that we're going to get at -115 kilopascals or -16.7 psi, we'll get 0.2 volts, and at the top end we'll get 4.6 volts. So we know that when we're vacuuming or suctioning from this port, the voltage is going to go down, and if we're adding positive pressure into this port from a vacuum, the voltage is going to go up. Also stated on the data sheet is the power requirements. The sensor will only be allowed to receive 5 volts, plus or minus 0.25 volts. So you'll have a range between 4.75 and 5.25. And this is why I'm using a voltage regulator that we've used in a previous video, or videos, of the 5 volt stable regulation. And I'm using the Maxim 603 chip to do this. We won't be using pin 1, which is located right here, and it's also the location where there's a slight angled portion on the sensor housing. Pin number 2 is the supply voltage, this VS. Pin 3 is ground. And pin 4 is the output voltage. We know that the output side of this chip is over here on the right hand side of the chip. This is the pin number 1 here, and a little dimple right here is showing you the orientation of the chip. And this pin here is the output for the regulator, and this is going to give me a 5 volt regulated voltage. This will go to the second pin, so let's go ahead and do that. And ground is going from this pin here. It can be either one of these 2 pins because the regulator always has the 2 middle pins as ground, to the pin number 3 here. Okay, so we have supply to the sensor. Now we're going to use a battery like this, a set of batteries. It's 4 batteries with 1.5 volts each, which makes 6 volts. And we'll plug that into the input side, and making sure that the red goes to the pin number 1 here, and the ground black goes to pin number 2. So now we're supplying voltage to the regulator, 6 volts in this case. Through the regulator we'll get 5 volts, and we're supplying the sensor. And now we just need to connect the probes of the oscilloscope and put a small tube or hose to the port of the sensor so we can measure some change in voltage. Let's go ahead and do that now. I'm using a silicone tube so it's easy to stretch. And that should be enough. So I'm just going to use this end of the tube and create some suction to see a change in voltage. So I'm going to take my probes here. I'll put the ground probe, which is the black lead, to ground. And I'm going to take the probe lead and put it on the 4th pin. Now you always use the probe and a hookup wire just to make it easy to put into a prototyping board. And let's check some of the voltage. So on the oscilloscope I have it in the mode to show measurement, and I'm showing 1 volt per division. We can see that it's showing 4.719 volts, which is a little higher than what the data sheet said it would show. And my 0 or 1, let me disconnect this so we can see where. Okay, so this is 0 volts here, or 100 millivolts, which is pretty close. So the 0 volts is on the second line here. I wanted to give it a bit of a chance if it wanted to go below that, which it probably won't. It won't. So we can see as much spread as possible, or as much resolution as possible. I put it on 1 volt per division. So I've plugged it back in, the probe, and you can see it's showing 4.72 volts. And I'm going to create a suction in the tube and see what happens. Okay, I did that and I was able to get down, let me see. I got down to about 3 volts. And you probably saw it stop or plateau at a certain point, and that was when I was just using my tongue to stop the pressure from escaping. From looking at these results, which essentially we could get from the data sheet, you can also use a multimeter to find this information. You don't need really a line to show you voltage. You can. It's nice to have a visual of that, but a multimeter would be fine to find out what voltages equal what amount of suction. We also found out from the voltages how we will apply it to the microcontroller. When we get into the microcontroller and start to do the ADC, we can use a real gauge to find out what the actual inches of mercury or psi or whatever is, to determine the conversion we need to do, or the algorithm we need to do in the microcontroller to show the correct value on the LCD. So let's go ahead and set up our initial circuit, which adds the sensor and the LCD to this breadboard. I want to add that the use of this particular microcontroller, which is the ATmega32, is probably overkill. I could probably make do with an AT tiny microcontroller to do the same thing and with just as much success. But since I am going to be providing more functions for the pick and place machine, I'll probably want to do some more programming and maybe add some more functions. So I'm going to leave the ATmega32 in this particular project just for expandability in mind. I'll also be using a relay that looks like this. A relay is generally just a device that if you apply 5 volts to it, in this particular case it's 5 volts. Relays come in various coil voltages, and that just means that if it's a 5 volt coil, then the switch will be activated when 5 volts is applied, and when 5 volts is not applied, the switch will open. And you can also get switches that are open when you apply the 5 volts. That would be called a normally closed switch. This particular switch is a normally open switch, and you can see that it actually says that here on the bottom. It's NO for normally open. So when you apply the 5 volts, it closes the switch and creates a connection between these two pins. These are the two pins that are considered the contacts, and these two pins are considered the coil. So you apply the ground and 5 volts to these two pins, and these two pins will connect together. If you disconnect the 5 volts from these two pins, or apply 0 volts, then these two pins would be open or not connected. To test to make sure that this relay is working, I'm going to plug this into the breadboard, and I'll just use the first pins here. And the pins are on either side of this breadboard, so they're not connecting. And I'm going to run the output, the 5 volt output, to one side. That'll be here. And then running it to the other end. And the pin is located on this strip. And then I'll take the ground, which is the next pin down here, and I'll put this on the other side. Actually, I'm not going to connect it yet. I'm going to show how it responds when I'm connecting it and disconnecting it. I'm going to go ahead and plug in the battery power, and you should hear a click when I apply it to the strip on the breadboard. There you go. So now the switch is closed, and now the switch is open. You can hear a click because there's an actual mechanical process happening. This is an electromechanical device. And when I click it and let it go, you can hear that clicking. That's the physical switch opening and closing, just like a light switch. Inside of this relay is a coil that pushes a pin up and down to actuate a lever of some sort that connects between the two pins here. So with this possibility, we can easily activate a switch from any of the pins of the microcontroller. If you are following along with these experiments or producing successful projects on your own, helped by these tutorials, please let me know using the Contact Us page on the newbiehack.com website. I would like to feature these on the website to benefit and motivate others to join this creative field. Thank you.